Well, good evening. Thank you so much for being here. We're almost like 3 days close to halving, so luckily we will have a Lambo pretty soon. So today we are going to talk about scaling Ethereum, the power of UTXO. Last November in L2 days in Istanbul, Vitalik made a panel, Bulletproof Vitalik. And I think there's two cool key takeaways from this talk. The first one is Vitalik mentioning plasma, which is pretty crazy because we know plasma just doesn't work. But Vitalik also mentioned UTXO, which is amazing because it's today's topic. So we are going to talk about the estate bloat issue and how it's threatening decentralization. We are going to talk about race condition and execution and why is that we cannot have parallel transactions in Ethereum. We are going to talk about UTXOs. We are having a quick review to the half-ini reusable proof of work, which is like solving the double spending and so on. We are having a quick view to the state minimized design. We are introducing predicates. And we are doing a quick overview of others alt VMs working with UTXOs in the space. So, state bloat and decentralization. State bloat is the issue where the hardware requirements for running a node keep increasing over time. In this way, making it harder for users to run their own nodes and therefore making the network more centralized. Basically, this is an issue to decentralization because if you don't have money to run a crazy expensive hardware, well, the network is going to be validated just by the biggest actors. We know this history because of Bitcoin as well. We have like the Bitcoin mining growing so fast that basically today is hard to mine a Bitcoin if you are not a professional miner. This is a random chart with no data, which basically means as a state grows within the Ethereum network, the hardware requirements are increasing as well, and there's a line where basically becomes expensive to run something to validate Ethereum. This is a more detailed chart. This was published by Paradigm, I think, 2 months ago, and basically showing how Ethereum state is growing over time. But there are multiple types of state, and we have to distinguish them in order to understand what's happening behind the state bloat issue. So we have a state growth, which is new accounts, bytecode, and storage. We have history growth, which is the storage of blocks and transactions. And then we have state access, which is the issue behind write and read operations in the process of building and validating blocks. Today we are going to focus in state growth, which is specifically new accounts, bytecode, and storage. This is information regarding execution environments. As today, Ethereum state is 245 gigabytes on a red node, which is a lot of information to be held by the nodes, and its distribution goes like this. We have accounts having a 14% of storage. Then we have bytecode having 4.3% of storage. And then we have contract storage, which is 81%. So it's a lot of information, a lot of hard drives just taking care of contract storage. Looks like it's fine, but it's not. So this is a more detailed look at the current situation of Ethereum state. This is also coming from Paradigm latest investigation. And as you can see, somewhere around 48% of all the storage in Ethereum is ERC-721 and ERC-20, which is basically we are taking half of the Ethereum storage just to track assets. Right now, we are going to stick with state bloat is bad because we are coming back to this, but before that, we are taking a look at the second problem I want to introduce today, which is the race condition and execution. So basically, why we cannot have parallel transactions in Ethereum. This is an Ethereum block header, has a lot of information, but like the relevant information here is the state root. As you might know, Ethereum storage is composed by Merkle trees. These Merkle trees are basically hashes of hashes and hashes up to the state root, which is a way to validate information quickly without having to take a look to all of the information of the chain. But if you have the time to decode all of this hashing, you will get something like this. This is a dictionary. This is how Ethereum state looks. And it's basically a collection of keys and values. Each key is your Ethereum address, and each value is your Ethereum, your Ether balance. When it comes to contracts, you have the contract address, you have the Ether balance for that address, and you have the storage root for that contract. So basically, you have this tree of hashes for the Ethereum storage. Well, inside each smart contract account, you have another tree having all of these contract storage information. And if you happen to decode that state root of the contract, you will see something like this. For an ERC20 contract, you just have accounts and balances for that specific token as well. So the question might be, why is that account model is a blocker for parallel execution? Well, because of race condition. This is a concept coming from computer science, and basically is a situation where you have two processes, and these processes are trying to access and update the same slot in memory. Because the virtual machine can know whether a transaction is going to update the same storage slot, Ethereum has the obligation to process every transaction in sequence. Looks like this: multiple contracts trying to update your balance at the same time. Back in 2017, the Ethereum core team tried to focus on this issue. This is a GitHub issue called Easy Parallelizability, and it's already closed, so was not solved. And basically says, this allows the EVM to be processed in parallel much more easily by specifying statically what addresses they can access. This is what is called an access control list. So basically, they were trying to implement some sort of data structure between the Ethereum transactions for the VM to know whether two transactions were going to update the same balance. Spoiler, it didn't happen. We have many interesting key takeaways from this issue. One of them is by Vitalik himself. One problem with these accounts is that accounts have arbitrarily large storage trees, and we cannot load that into memory. As you might see, when you are trying to validate Ethereum state, you have just the state root. You know that there's information being between that hash, but you don't know whether it's going to be huge or not. Another nice takeaway from this issue is Vitalik suggesting that we require nodes to have 512 gigabytes of RAM. This is what I'm talking about. Like, if you're trying to build nodes like this, you cannot expect to have decentralization, because nobody in the retail space is able to like run this kind of hardware. So basically, in 2018, the issue was closed. The conclusion was that sharding and stateless clients is the way. So you don't have parallel transaction in Ethereum, but you can have like a less heavy Ethereum. So as you might see, 6 years ago, Ethereum understood this, and it's that stateless is the way. So right now, let's keep this information, which is account model is somehow bad. Then it comes the UTXO model, which comes as a blessing. This is Hal Finney giving us computer nerds the UTXOs. And basically, the UTXO has this power of avoiding the necessity to have a root state. So you don't have a centralized source of information containing the balances of all accounts, because UTXO handled that problem differently. The UTXOs are basically the transaction model used by Bitcoin, and looks like this. You have transactions, and these transactions have inputs and outputs. So the UTXO might be like a piggy bank. So you put money inside a piggy bank, and that piggy bank has a balance. And for your account, you have multiple piggy banks. If you want to spend one of these piggy banks, you have to destroy it completely, as many as you need, and create a new piggy bank that you are going to send to the recipient of the transaction. Looks like paying with cash. So you have a $100 bill, you give that to the cashier, and you get maybe 30 in return. So you are giving one bill and receiving different bills. The difference might be that in a UTXO scenario, the cashier is going to burn the bill they received and creating new bills from scratch, therefore avoiding the double spending issue. So basically, in the UTXO model, you have like each transaction is having multiple UTXOs as inputs. The transaction is destroying those UTXOs and creating a new UTXO as a result. A more detailed look might be this one, where you have like 50 BTC coming into one transaction. This transaction is splitting 0.5 into another transaction and keeping 49 and 5 for the owner. So basically, this is you having 50 BTCs and spending just 0.5. One is going to the next transaction, the other one is being kept in your address. In the second transaction, somebody is trying to spend 0.8, so it's combining one UTXO of 0.5, another of 0.8, and another of 0.3. These are being destroyed and merged into these new UTXOs. So the question might be, how is that UTXO allow parallelization in Ethereum? Well, because you remember the race condition. For UTXO, you have atomic state. This means you don't have a central place where the information is being stored, but you have pieces of a state floating around in the protocol and being used in each transaction. So again, the UTXO is killing the necessity of having a root state. But I have an announcement to make. I'm Sandusky. I'm developer relations at Fuel Network. This is my Twitter, if you happen to want to follow me. We are building an amazing technology we have called the Rollup OS for Ethereum. This is kind of a framework to build execution layers for Ethereum following the modular approach that was discussed here in the previous talk. So yeah, that's the sales pitch. Let's follow up. So we were talking about how UTXO is so good. And I think it's important to mention that this UTXO idea comes from a really cypherpunk background. It was called Reusable Proof of Work by Hal Finney back in 2003, I think. So this is the actual banner of the website. This is something that is available online at nakamotoinstitute.org. They kind of archived the original website of this project. And basically, reusable proof of work relies on Adam Back work. So Adam Back basically was the guy who invented proof of work as a way to avoid spam on email. So if you want to send me an email, you have to spend money basically creating a hash with trailing zeros and so on. But Hal Finney realized that if you are receiving a lot of this tokenized computation, means that you are a real person, because somebody who is sending a spam is not receiving any email, therefore is not receiving any tokenized computation. So I was like, what if we can exchange these proof of work tokens? What if I can use my own reputation to send emails to another person. So if I'm willing to send you an email, I don't have to prove that I'm a real person because I already have some tokenized computing. Well, this is when Halfini designed this concept of reusable proof of works. Fun fact, this is the original slides used by Halfini, and they are available online. So basically, they are having like the hash cash, which is this tokenized computation proof of work, and then you have the reusable tokens. These tokens are being verified by a decentralized network of nodes having a common protocol in order to create new reusable tokens. How to avoid these tokens to be expended twice? Well, by destroying them and creating new ones, each on each validation. This is like the Bitcoin network in one slide. You have proof of work, you have tokens, you have servers, decentralized ledger, and exchanging of tokenized computation. So thank you so much, Halfini, for building this technology for us. So let's come back. So we were talking about state bloat, we were talking about parallel execution, and we were talking about how UTXO might solve that. But in practical terms, the actual way of solving that is by using a state minimized design in our applications. So right now we are having a network of applications in DeFi and so on, relying mostly on a state for their transactions. This approach states that you should use more bandwidth in order to reuse the state. So let's take a closer look on how memory works in Ethereum. In one side, you have cold data and memory, which is information to be used just in the context of the transaction. Cold data specifically is read-only information that comes within the transaction. It means that this is information coming from outside of the chain. And then you have this storage, which is the information that you are storing permanently in the chain, and we know that's an issue. So we are pressing this button. You can think in a storage-based design as going to a restaurant. You walk the streets of your city, very lightweight, not carrying anything around, and you go to that place and they have the food and you eat. So you are sending pretty lightweight transactions and you are getting into the contract and they have the information there for you. In a state minimized design, you are keeping the information with you all the time and going to places and having you ready to eat meals. So basically, you are sending a lot of information in the cold data and you are keeping a little bit of storage on each contract in order to avoid having a state bloat on the system. Uniswap v3 is actually doing this. This is the staker, like a section of the staker of the Uniswap v3. And basically, they have a getter function, which is get reward info. And this function is actually computing, dehashing some kind of compressed information in the storage each time somebody is reading. And this might seem like a nonsense because we learned that in computing, we want to avoid computation. So we create caching and a lot of stuff, and basically, we want to avoid computing many times stuff. In this way, we rely on storage. But for blockchain, actually makes sense to go the other way around. So you are having a small section, a small piece of information in the storage, and you are spending more resources on execution. That's the key. More execution, less storage. And this is called a state hydration. You can find similar concepts in front-end applications right now, like after Next.js 12, like they start making these static websites who load faster, and then you are using some JavaScript magic in order to like rehydrate the state. Well, it's something similar. And in Fuel Network, we merged this state minimized approach and the UTXO model to create predicates, which are stateless account abstraction. So we were talking about UTXOs as a way to have like parallel transactions and so on, and not having a state bloat and centralized state. And I just mentioned predicates, which is a stateless account abstraction. Well, just in the middle, we have pay-to-script hash. This is an amazing technology. I think was BIP 16 by Gavin Anderson. And you might be wondering, what is this? What is in the middle of the study? Well, you know, like the standard approach of creating accounts. You have private keys, you have an elliptic curve, and you have the public key. This is like a standard EOA account on Ethereum. Well, the pay-to-script hash account looks like this. You have a couple of signatures, you have a script, and by hashing this, you have a script hash. So the public address, this is a special type of account on Bitcoin. The public address is not coming from a private key who a human being is holding, but it's coming from a script. And this is like the powerful concept. It's like code owning assets. Looks like a lockbox, the kind of lockbox you use for Airbnbs. So you have some kind of device floating around in your protocol, and then you have some kind of puzzle or challenge to be solved. And if you happen to be able to solve this challenge, you are getting the asset. It's not somebody giving you the asset. It's a machine giving you the asset. So in this case, the redeem script will be that challenge who is like keeping that asset, and then you have the keys. So why is the issue behind pay-to-script hash, and why is not something widely used right now? Well, because Bitcoin is not as powerful. Like, you just have the Bitcoin script, you don't have a expressive and powerful VM. So Ethereum had that power, but Ethereum having a powerful VM lacks of parallel transaction and a state minimized design because it doesn't have UTXO incorporated. Then it's when it comes predicates, like solving Bitcoin issues by coming into Ethereum and having a powerful VM, and solving Ethereum issues by implementing a stateless account abstraction code that owns assets and so on. So let's talk about predicates. Predicates is like mixing the UTXO approach, a powerful VM such as the Fuel VM, the Swaylang, which is a Rust-based DSL, and the concepts behind pay-to-script hash. That is how you get predicates. A predicate, it's a pure function giving a Boolean return. This code is being hashed with the Sway compiler, and you are getting a public address. So the source code is the private key. Predicates are like wallets. They can receive assets, they can hold assets, they can spend assets, but as wallets, they cannot be deployed and they cannot be deleted. So predicates are pure functions with a Boolean return, and if a client wants to spend these assets, does a process called evaluation, where you run the script, the predicate script, and therefore can transfer the assets. So the predicate has some condition of if the transaction is fulfilling those conditions, the assets are going to be freed. So I'm reutilizing this slide where how you can spend a predicate. You have the predicate code, so this is something outside the chain, like the chains doesn't need to know the predicate code. So this is like call data you are providing to the client. You have the transaction that fulfills that condition, so maybe some asset being incorporated into the transaction, I don't know. And then you have a UTXO set and a network of few clients trying to execute this code, trying to fulfill that condition with this transaction, and as a result, you get a new UTXO. So basically, this is some kind of device in the blockchain that holds assets and spends those assets. Predicates are stateless by design. So you cannot access data on chain, you cannot read from smart contracts, you cannot check date or time, or you cannot read block hash or numbers, but you can read input and output coins and transaction scripts and transaction bytecode. Actually, this was taken from our guide, Predicates 101, Building a Stateless DeFi Applications. You can check this QR code if you want to start building predicates. And as a bonus track, some VMs using UTXO. So you have Aztec, you have Nervos, which is like an intent-based network. You have Findora, and you have Alephium. So all of these people are using UTXO, but only Fuel is using predicates. So some conclusions. State bloat is an issue. Ethereum is not parallel. UTXO is really good. Halfini, thank you so much. You have this amazing mix, which is predicates. And if you want to start building a state minimized application, come to this link. And thank you so much for coming.
All right, does anybody have any questions? We have time for 1 or 2 questions.
Well, if you happen to have some questions, you can find me around and we can spend more time nerding around account models and storage and so on.
Thank you very much.
Thank you again.